Well, greetings everybody. So today we'll be talking about annuities, okay? And the reason I'm bringing this up at this point in the class is because there are some related concepts that I think it'd be good to cover first, which we have recently done. If you're going through the assignments in order, and those related concepts are compound interest and geometric series, okay? So both of those I've had assignments and videos posted recently to involve them. Okay, but let's talk about annuities, and I'll show you along the way how these concepts are related. All right, so let's talk about regarding an annuity. What are the vocabulary and concepts related to that? Okay, so first of all, an annuity is just a series of equal payments made at equal periods of time. Uh, so if the payments were unequal or scattered out irregularly over time, then we wouldn't be considering that an annuity. Equal payments made over equal periods of time. And I'll give you examples of that, of course, but hopefully this is basic enough for now that you at least got the basic notion. Okay. Now, if we're going to make equal payments over equal periods of time, there's going to be something called a payment period. That's going to be the time between payments. So we might make a payment every month or every quarter or every year or whatever. Okay. All right. And then if we take that a little bit further, there's something called the term. That's the time between the beginning of the first payment period and the end of the last period. So, you know, if you say I'll deposit a payment in my bank account every month for a year, then I'll start, and at the end of the first month I'll make that payment, and at the end of the second month I'll make the payment. But for the total time between when I made that decision to do that and the last payment would be a year. That would be the term. Okay. Now there are variations of this. Okay, and I'll say that in this video, in our class this semester, or let's say at least right now, we're gonna study something called an ordinary annuity. Okay, so that is an annuity where the payments are going to be made at the end of each period, because so far my vocabulary is left that open. I just said you make a series of equal payments at equal periods of time. I mean, with the example I used a minute ago, we could make a monthly payment into our bank account, all right, for a year. Do you pay that at the beginning of the month or the end of the month? Okay, as I had described it up here, I mean, it could be either way. But an ordinary annuity, the payments are made at the end of each period. Okay, so if we made it at the payments at the beginning of each period, it would change the formulas that I'm going to show you a little bit. All right, so we'll just talk about an ordinary annuity. Payments will be made at the end of each period. And also, the frequency of payments is the same as the compounding frequency. Okay, now I haven't really told you how compound interest ties into this yet, but it won't just be that we're going to make the payments and then they add up. It will be that we're going to make the payments and they will add up, but they will also accumulate interest along the way. Okay, so if you had a bank account and you earned interest at a certain rate, you're going to put the payments in there, but the money that sits in there earns interest just for sitting in there. Okay, so that's how compound interest ties into this. So we got two things happening. We got the payments being made, and then we got, once the payments are made, they accumulate interest. Okay, all right, so that's what I mean when I say the frequency of payments is the same as the compound frequency. All right, now at this point, we cannot talk about it anymore. Got to see an example. At some point we got to look at examples to really understand what all the concepts are. So here's a basic example that I want to go through in a lot of detail, and I want to do some very specific calculations for you to understand how an annuity would work as I've described it so far. So let's say that you're going to deposit $1,500 into an account at the end of each year. Now remember, in an ordinary annuity, we make the payments at the end of each period. So into an account at the end of each year for 4 years, the account earns 2% interest compounded annually. Okay, so we're going to make the payments at the same frequency as the interest is compounded. Okay, so we make the payment at the end of the year, the interest is compounded yearly also. Calculate the future value of this annuity. Now, the future value is just what you end up with all the payments and all the interest they earn added together. Let's talk about how that would happen. So here I have a horizontal line that just represents time. Okay, so there's 0 when you decide to do this, and then you make the first payment at the end of the first year, and you make the second one at the end of the second year, and that goes on for 4 years, and then it's all over at the end of the 4th year. Now, let's think about how this would happen in detail. Now, I'm going through this in detail. It might be more detailed than you want to hear, but I want you to know what's happening along the way, how the interest is factored in, and so on. Okay? So, at the end of the first year, you make the first payment. That's $1,500. But, remember what I said? That the money that's sitting in the account will grow. It will earn interest. Okay? So it's not like when you make that first payment of $1,500 that it just sits there for 3 years. It will grow for 3 years. Okay? It will earn interest at 2% compounded annually. All right, so as I calculate the future value, like the grand total, the amount of money that's in this account, considering all the payments and all the interest, I have to account for that $1,500 earning compound interest at 2% per year, compounded annually for 3 years. Remember that formula right there? That's our compound interest formula. P is principal, that's the amount that's earning the interest. R is the interest rate, the annual rate. N is the number of compounding periods per year. Okay? And then T is the total number of years. All right, so that was our formula, so I'm going to apply that here. So $1,500, okay, earning interest at 2% for a year. For 3 years is going to be 1,500 times 1 plus 0.02 over 1 to the power 1 times 3. Okay, so that's how much it's worth at the end of this, the 4th year, the last payment of the annuity after that's made. That's how much this first payment becomes worth. Okay, now at the end of the 2nd year, I make another payment, but it grows for 2 years in the same way, compound interest. Okay, 2% per year, compounded annually for 2 years. That's what that formula is. And then at the end of the 3rd year, I make one more payment of $1,500. It grows for 1 year. So again, I calculate 1 year of interest on that. So that's 3 years of interest on the first payment, 2 years of interest on the second, 1 year of interest on the third, and then the 4th and last payment is just a deposit only. It doesn't grow. Okay, that's what's happening. That's how all the payments are going in, and that's how they are accumulating interest by themselves. All right. Now, the grand total, the future value, would be this number. Okay, 1,500. I simplified a little bit, 1.02 to the 3rd power, plus this number, 1,500 times 1.02 to the 2nd power, and so on and so on. So there all of them are. Okay. Now, what that turns out to be is a geometric series. So remember at the beginning I said related concepts to annuities are compound interest and geometric series. Okay, so you could add all this up by brute force. If I wanted to, I could take my calculator and add it all up. It's not that big of a deal, but this is normally taught with reference to geometric series, and so that's because that's what people normally do. That's what I'll do for you. So that's a geometric series. We'll have to consider this as the first term is 1,500 and R is 1.02. Well, real quick, what is a geometric series? A geometric series is a series where you take any term and you multiply it by the same number and you get the next term. So if I took this term and I multiplied it by 1.02, I would get this one. And if I multiplied that one by 1.02, I would get this one, and so on. So that's what a geometric series is. The sum of n terms of a geometric series is a1 the first term, times 1 minus r to the n power over 1 minus r. So that gives me a formula to calculate the grand total of this, which is how I said we would do it, at least for now. Okay, so that'd be 1500 1 minus 1.02 to the fourth power. There's 4 terms I'm adding together here, over 1 minus 1.02, and that turns out to be $6,182.41 if you round to the nearest penny. Okay, all right. Now, if you wanted to right now, you could take this and this, get your calculator, add all this together, see that you get that same number. All right, but I want you to see that it's also a geometric series, and we can use our thinking and formulas that we learned when we studied that to apply to this. Now, real quick, before we leave this and look at some examples and other formulas. So remember that we have two things happening. We have the payments, and then we have the interest that they earn. And I tried to map that out with this diagram right here so that you could have a way to think about all of it. But another way that we could just see this number is, look, that number, the future value, a certain amount of it is because of the payments, and then the rest of it is because of the interest. So think about it real quick. In case you have to break this down at some point, I'm making $1,500 payments that leave my pocket. All right, so how much in payments went into this account? Well, I made 4 payments. 4 times 1,500, that's 6,000. So I made $6,000 of payments. So it must be that where'd that other $182.41 come from? That was the interest they earned. Okay, this one earned some interest, this one earned some interest, and this one earned some interest. And between those three, it came up to be like $182 of interest. All right. So yes, if we can break that down into the raw payments that went in and the interest that they earned. All right. So let's look at this. Now, it's not that every single problem you see, I want you to think about in terms of a geometric series. I want you to understand it in terms of what an annuity is if you break it down and write it all out. It is just a geometric series. Okay? So when we were studying geometric series, if you thought this can't possibly apply to anything, well, if we have an annuity, then an annuity turns out to be a geometric series. But let's take just a basic formula that will get us the future value. Okay? All right, so here is the formula for the future value of an ordinary annuity. And because maybe these terms are new to us, remember, an ordinary annuity is when payments are made, at equal periods of time, equal payments, equal periods of time, but at the end of each period. All right? So the formula for the future value of an ordinary annuity is that the future value is equal to the payment, whatever those regular payments are, those regular and equal payments, times 1 plus r over n. Now r is the annual interest rate that's given, n is the number of periods that there will be in a year. So like if we were making these payments quarterly, there would be 4 per year, to the power k, where k is the total number of periods. We'll look at some examples to calculate k, minus 1 divided by r, the interest rate, divided by n, the number of periods. There it is. Now, if you had a very basic calculator and you were trying to do this with like the simplest of scientific calculators, you may run into some trouble with rounding error in my math lab. So let me just say this. I don't think many people will have calculators that make this difficult, but how about I'll just say that if you need help with your calculator, just ask, and then I can go over it with whatever you're using. All right. Okay, so let's try this. How about this? Let's try to verify that number that we got, when I work this one the long way. Here I work this one the long way because, I just feel like you need to understand what's happening, okay? And if all you do is plug numbers into a formula without thinking about what's going on, then I don't think you understand it all the way, okay? So, but let's see if we can verify this number. I'm going to take the same scenario, the same annuity, and I'm just going to use this formula right here to make sure that I could do that to verify this number. Okay, so here goes. Once again, $1,500 is deposited into an account at the end of each year for 4 years. We earn 2% interest compounded annually. Calculate the future value. All right, well, the payment's $1,500. The interest rate as a decimal, 0.02. We're going to have one compounding or one period per year. Okay, so if we're going to make our payments annually, that's going to be one per year. And K, what was that number K? That was the total number of periods. Okay, well, so if we deposit into an account each year, at the end of each year for 4 years, there will be 4 total periods. Okay, so here's all those numbers going in. Okay, and I'll reduce a little bit. I get 0.02 over 1. I get 1.02 to the 4th power minus 1 over 2. That turns out, if you calculate that, $6,182.41. That's the exact number that I got when I thought it all out up here. Okay. All right. Now let's look at a few more examples real quick. And these I've taken from our assignment. So this one is fairly straightforward in terms of taking our numbers and plugging them into our formula. All right, but I've got to make sure that you can do that with your calculator. Okay, so it says find the future value. Okay, we know what that is. That's how whatever is in the account, payments and interest all considered. Okay, we have an ordinary annuity. That's kind of annuities we're talking about. So we're going to make payments equal in the regular payments of $2,200 at 1.65% compounded monthly for 7 years. Okay, so let's think about it. The payment is just given out up front to be $2,200. The rate, okay, 1.65% as a decimal, 0.0165. Okay. If I'm going to make, say my payments are monthly, then there would be 12 periods per year, right? 12 payments per year. N is the number of periods per year. All right. And then what was K? K was the total number of periods. So if I make payments monthly for 7 years, okay, so that'd be 12 times per year for 7 years, then the total number of periods is 7 times 12. That's going to be 84. So there's everything that goes into our formula. That's what it looks like when it goes in. Now, if you wanted to, when you put this in your calculator, you see how I have like parentheses and brackets this way? If you wanted to, you could put it in like that. That's one way to do it and see that you get that number. All right, but like I said, everybody's got a different calculator. It's hard for me to give general advice beyond that, so if you're having trouble working this out with your calculator, let me know. All right, okay, so this one goes straight in like that. Now let's look at one that involves a little more thinking about what's happening. Okay, so in this one, over the period of 27 years, I have 2 annuities in sequence. Okay, so it says that for, say, the first 12 years, I'm going to pay $1,000 per quarter at 6.1% compounded quarterly. Then, after that, after I make that last payment of $1,000 at the end of the last quarter, at the end of the last period, at the end of 12 years, everything changes. Then I make $1,700 per quarter, invested at 6.5% compounded quarterly. So it's like after, it's like after the first 12 years, after the first annuity, the payment and the rate change. Okay? All right, that's what it says. Now, how about this? Rather than think this all through right now, how about we just figure out what each one of these is going to be worth on its own? Okay, so in other words, if I pay $1,000 per quarter at 6.1% compound quarterly for 12 years, then we could use that formula I introduced above to figure out what that all is going to be worth at the end of 12 years, right? So we have a payment of $1,000 per period. R, the rate, 0.061. If we compound quarterly and if we make our payments per quarter, that's 4 periods per year. There are 4 quarters in a year. And if I make quarterly payments for 12 years, how many payments will there be? How many periods? Well, 4 payments per year, 4 times 12 years, that'll be 48 payments total. Now, if all that goes into my formula, then here's what those payments plus the interest they earn are worth when all that's over. It's a little more than $70,000. Okay? So that first annuity, which goes on for 12 years, that's what it's worth. Now, let's forget about that one and calculate this other one. So what if I pay $1,700 per quarter at 7.5% compounded quarterly for 15 years? Well, that on its own looks like this. 1,700 payment, R 0.075, N is 4 because there's 4 quarters per year. K, what's K? Well, K is however many payments there are going to be. So if I make quarterly payments for 15 years, 4 times a year for 15 years, 4 times 15 is 60 total periods, 60 total payments. So suppose I put that in, then here's what these payments and their interest are worth at the end of 15 years. Future value, 1,700 times all that. That's that formula I introduced above. So these payments and all their interest are worth like $185,000. All right, now think about real quick, what would we do to get the final answer? What is all of this going to be worth? These payments and their interest and these payments and their interest, would you just add these together? Okay, is that what you'd do? I think it would be tempting to think that you would add them together, maybe in hopes that things would be nice and simple. You would think that we'll just add these together, but it'll be more complicated than that. And here's why that is, okay? So I drew a little diagram here to help you think about it. So this red horizontal axis is time in years. So we were going to make our $1,000 payments at 6.1% compounded quarterly for 12 years, okay? And then that was going to amount to about $70,000, all right? And then after that, everything changed. We made payments of like, what was it, $1,700 at 7.5% compounded quarterly, and we did that for 15 more years, and that'd be 27 years into the future from the beginning. The thing is that this money is in the account, like the future value of that first annuity, and it just sits there. What happens to that? Well, money in the account earns interest. So this money that was in there at the end of that first 12 years grows according to however the account was earning interest for the next 15, okay? So it's not that we can just add these two together. We have to think, well, this one's growing while these other payments are being made, all right? So as we calculate the growth on that, that would just be ordinary compound interest. You go in to this 15 years, this next annuity, with that amount of money just sitting there, earning compound interest according to our formula that we learned when we first learned about compound interest. Principal 70,018 times 1 plus R the rate. Now at this point, once that's the end result of the first annuity, we get 7.5% compounded quarterly, so 0.075 over 4 times R to the power NT, 4 times 15. So that's what that's worth. Now right there, I forgot to put the 23 cents, okay, but yeah, the 23 cents goes in there, okay? All right, so that's what it ends up being worth, and then we'll take that number and add it to this other one, okay? So all these payments are made, they're worth this much, but then they grow like that, okay, and that's part of our answer. And then this other series of payments are made, and between all of them and the interest they earn, they become this. So we'll add those two together, and you'll get, if you round it to the nearest dollar, just short of $400,000, $399,148. Okay, so that one has this extra wrinkle to it, that I can't just think about my formulas and plugging numbers into it. I got to think that, well, here's what's happening. You know, you get certain dollar amounts along the way, but you have to consider that more goes on beyond that. Okay, so I'll leave you with that to practice some of these problems. The only thing I'm uncertain about is if you'll have trouble with your calculator. So I already told you I won't say anything more about that, but let me emphasize, if when you're doing the problems and they say, for example, round to the nearest penny right here, and it says don't round until your final answer. If you round a lot of these numbers along the way, you introduce round off error, and if you do calculations with a rounded number, you just magnify the error. So if you feel like you're doing it right, but My Math Lab keeps counting it wrong, it's probably because of you're having trouble using your calculator, you're rounding numbers too much along the way, and so on. In that case, just mention it to me.